Okay, so welcome all to the third and final day of the workshop. So hope you're having some nice time and also gained some knowledge about different learning algorithms. So what I will do is, so I'm going to do some basics of another key learning algorithm known as reinforcement learning, right? So you talked about supervised learning, unsupervised, and so on. And Dr. Pooja talked about distributed learning. So here I'll talk about reinforcement learning. Okay. Yeah. Before proceeding, so I'll just like to show this slide here. So it's about the models of machine learning. Okay. So we have been listening to different talks, right? And also we had a keynote talk where Professor Narayana argued that none of these are actual learning methods. But nevertheless, we will do our duty of sharing whatever knowledge we know. Okay, right. So yeah, as again other speakers also have mentioned, but just for completeness, again I'll very briefly discuss. So what you do in supervised learning is they're essentially like a supervisor who can give you the correct feedback about your actions, right? Whether you are right or wrong. So you will get that feedback here. So in the case of unsupervised learning, what you have is you have a data set and you will essentially do some labeling without any supervision, essentially like a classification problem. So I'm not from these areas, so I may be a bit different about using the terms here, but the essential idea is the same. So in the case of semi-supervised learning, so you have a data set and partly you will be supervised and the rest of the data set you are supposed to make predictions. Okay. Whereas in the case of reinforcement learning, or in many instances, what will happen is, so there is no data set at your disposal, and as Dr. Manjesh also was mentioning, right, in the case of online learning, from day 1 or day 0 onwards, you should start learning. Okay, so that's about reinforcement learning. Okay, so there is no supervisor or no data set at your disposal. Okay, and moreover, even if so it's not so unlike in many cases where there is a ground truth, so there is no ground truth here. Okay, that's something you have to learn over time, right? So we'll talk about reinforcement learning. So this is the outline. So essentially what I will do is I'll talk about few examples where reinforcement learning can be applied. Okay, and then so I essentially come from this say MDP background. So this forms as the mathematical basis for reinforcement learning. Okay, so you can look at RL as an algorithm, simple iterative algorithm. But so why that algorithm? So all the theory behind theory for reinforcement learning comes from this theory of Markov decision processes. Okay, so I'll talk about MDP formulation. And then take you naturally into reinforcement learning. Okay, and then we'll look at application of this to the area of wireless network. So I work in the area of wireless network. So we'll look at a problem of achieving coexistence between LTE and Wi-Fi, right, using techniques from RL, right. And I think in the afternoon session, Dr. Chitraganti is from IIT Palakkad. Okay, so he's going to talk about application from the context of or from the area of control systems. Okay, so that way you will get two different applications about RL. Okay, so let's start with some example scenarios. Okay, so these are some popular examples that that's always discussed. So take this example of inventory control. Okay, so suppose you have a store or it could be a cloth shop, or it could be a big warehouse also. Okay, so where you are ordering items, customers are arriving and some items are being purchased. Okay, and end of the day you have to decide, right? So you may have some amount of items left with you. So you have to take a decision of how many to order, right? It could be day, or if it's a very big warehouse, it could be the duration could be a month. End of the month, you have to decide how many to order for the coming month. Okay, so that's a very simple. So sounds like a simple decision, but your arrivals are random. So you don't know. For instance, if you have a car showroom, you don't know how many cars will be booked in that particular month. Okay, right? So you have to make a decision in kind of uncertainty. Okay, so even in the case of restaurant, right? So you have let's say you are preparing some dish, so you have to decide how many to prepare for that day. Okay, so the number of customers are random, right? If you prepare too less and if too many come, right? So you're actually at loss, right? You're not serving the business sufficiently. Now if you cook too large, there will be surplus, okay? So that's also a wastage of resources and money, okay? So that way, what quantity of stocks to order each day or each month, okay? So some kind of timeline, right? So I'll formalize this framework also in a while, but just so have this application in mind, okay? So this is inventory control, right? So you can stop me anytime if you have any queries, okay? So please feel free to interrupt. So we'll discuss and then proceed further, okay? Right. So the other example is this machine replacement or machine servicing, okay? So let's say there is a huge factory. So there is some machine that is operational, right? So maybe some small breakdown occurs in the machine, right? You can get it serviced or you can wait for some more time. Getting it serviced means you have to lose 1 or 2 days, right? So that will, your production is going to get hit. So maybe if the repair is very minor, you might still wish to proceed further, right? So you can delay your servicing for few more days, right? So similarly, it happens particularly with the car, right? Once you get it serviced, so it's in very good condition. So after some wear and tear, you know that there is some fault, right? But sometimes you will try to ignore the fault and wait for some more time, right? So going to service is going to cost you, okay? So maybe a simple fault like indicator not working, okay, or so on. So you will ignore that and try to delay going to a service, okay? So the question like when to go for replacement or service, right? So that's a decision you have to make, okay? So because service is going to cost you, right? And also operating when the car is not good is also not productive, right? So there's a trade-off between service and not to take your vehicle or machine for service, okay? So this is a machine replacement example. So another popular example is queue control, okay? So let's say you have a bank, or so it could be like some number of jobs actually lined up, okay? And then so it could be in many contexts, okay? So let's say in software, so some number of projects are lined up, okay? So in construction, some number of tasks are there, okay? So it's getting piled up. Now what you do is the question is it depends on who you hire, right? So you can hire a very skilled person who can really serve much faster, okay? But he will cost more. He or she is going to cost you more, okay? Or you can work with a not so skilled person. They may not charge you more, but the way of processing tasks is not very fast, okay? So there is delay you have to bear with, okay? So now there is again a trade-off, right? What expertise of server to employ in such scenarios, okay? So they are very simple models, okay? So I'll also talk about the mathematical models. Very simple decisions you have to take, but still you do not know what is the right decision when uncertainty is there, okay? So essentially like there's no ground truth for you, right? And you have to learn it over time, okay? So now all these problems that I talked about, right? So these are essentially sequential decision problems, sequential decision making problems, okay? So what it has is essentially there is a system and you have to decide the input for the system. So there will be some output, but there is also going to be noise, right, which is not in your control, right? And given the state of the system, again, so some controller you have to build which will decide what should be the input to the system, right? So you have to drive the system to some optimality in some fashion, okay? So essentially in these sequential decision problems, there are 4 or 5 ingredients to understand or to model a problem, right, as a sequential decision problem. One is you should be clear about what should be the state of the system, okay? So I'll call that as xk is the state of the system at time k, right? So this time k, I'm just talking about discrete time. So there are continuous counterparts also, which becomes theoretically more involved, but essential idea will be the same, okay? So time k, so in different contexts, time could be different. So one day could be, you count it in terms of days. In other applications, you may count it in terms of months. In much finer applications, it could be of the order of seconds also, right? Suppose you are transmitting bits, right? So in 1 second, you can transmit millions of bits, and maybe you are interested in how the number of errors that occurs in the transmitted bits. You want to control that, Okay. So, this time depends on the application of interest. So, the next component of a sequential decision problem is this action that you wish to take. Okay. So, there is an action that you wish to take. So, state action pair is there, and then there is random disturbance that is added to the system. So, which is not in your control, and learning is mostly about this random disturbance. Okay. Then the another key component of any system, it's an IO system, right. So, you should have some way of mapping the input to the output. Okay. So, this is your current state. So, this is going to be your current action. So, then there is some randomness here, and that will drive you to the next state. So, the state is not deterministic like the simple IO system that you study in a signal processing, right, signals and systems. The state is not a deterministic function of the current state and current action declared by randomness. Okay. So, decided by the amount of randomness there. So, this is state evolution. And finally, so the one more component which is not shown here is, so there is some kind of reward or cost that you are going to incur during each time. Okay. So, when you are in this state, let us say you place this action, so the reward incurred or cost incurred, right. So, this is the key component that will enable you to learn about the system. Okay. Now, one important point is I have not shown WK here. So, you just think of it as the average reward that you are going to incur. Okay. So, this is I have just incorporated it into this cost term itself. Okay. So, in general it could be function of WK also. I have just taken expectation of all possible WKs and just this is the average reward. Okay. Right. So, let us see in this context of inventory control. So, what is my state here? So, state is the available stock in your warehouse. Okay. I am just assuming a very simple model. So, let us say you have warehouse and there is only one kind of stock that you pile up in your warehouse. Okay. Only one kind of stock, you can always generalize it. Okay. So, one item, right, and you have some amount of item, and I am just allowing for negative, it says the backlog. Okay. So, suppose you have a car showroom. So, there may be some backlog at the end of the month. Okay. So, maybe some 2 customers have ordered and that has to be delivered. Now, you have to take care of that, and in addition to anticipating what you will see in the future also, right. So, that is it's a simple model. Okay. So, I am just calling that as the available stock, allowing for negative also. Then order to be placed, let us say at the end of the month you can decide how many cars you will order for. Okay. So, suppose you have surplus, you will wish to not order any car. Okay. And then so on. And then what is the randomness here? So, WK is essentially the random demand that is going to arrive in that particular month, right. So, you do not know how many customers will arrive for that to purchase that car. So, that is your WK here. So, now, so what you have, so what is the state evolution? I have just shown a very simple model. See, this is the available stock with you, this is the amount you will order. Okay. And this is what was the demand in that particular month. So, end of the next month, so this is what you have in hand. Okay. So, very simple linear model I am assuming here. So, even for models of this nature, now it is not easy to tell how many to order. Okay. So, very simple the only the decisions are of this order, this form, right. Still not easy to make decision here, not easy to tell what is optimal. Okay. Yeah, one more final component is this cost actually. So, essentially when you have a problem, so you have to model some cost that will give you feedback, right. So, suppose when the one step, so I am calling it as the one step cost, right, because it is the cost incurred in this stage, it does not account for the cost that you are going to incur in the subsequent stages. Okay. So, I am just assuming a simple model like this. Okay. So, what is this, how to understand this? So, let us say R of xk, right. So, xk is essentially the holding or shortage cost, right. See, what would be an ideal practice would be, let us say at the end of the month, your car showroom, right, you end up with 0 cars. That means whatever you got that month is sold out, right. That is the perfect scenario. You can there is no storage, no need for security or anything, right. So, you can just for 1-2 days, close your showroom, right? Need not worry about anything, right? So that is the holding cost. And shortage cost is you may lose potential customers, right? Because you have maybe there are two customers who have made a booking and you are not able to service them. Okay, so that is like the shortage cost, right? And then see, one solution could be, why not order some 100 cars, go ahead and order, right? So now there is a cost per unit item also, right? So there is always, so money is involved. So you have to nicely trade off between these two quantities, right? So you cannot order too many, you cannot order too conservatively also. If you order too less, right, so people will not turn up to your showroom, because every time you are sold out, it is not not good. Okay, right? So that's about inventory control. So similarly, let's go ahead. So machine replacement. So the problem I explained was very generic. So we'll try to model. So this is an attempt to model a scenario, right? So so let's say there is there's some machine, some car. Okay, so it may have n different states, right? I'll identify n different states, and each state represents the condition of the machine during period k, right? Maybe in that week, particular week. So this was the condition of the machine. And now there is an operating cost. Let's say state 1 is a perfectly good condition, right? So you just got your car out of service, or it's a new car. Okay, so it's in very good condition. So the operating cost is low, right? And let's say this capital N is the worst condition or the breakdown condition. So car is completely broken down. So this is the worst condition. The cost, operating cost, is very high, right? So suppose your car breaks down, so you have to now tow it. Okay, so you to get it to the service center. So there is a huge cost here. So in between there may so many other states. For instance, as I was mentioning, no, maybe the indicator is not working. Okay, so that's maybe acceptable, and you can still keep operating, right? Maybe a slightly higher cost of operation is there. Maybe the mileage is slightly hit, right? Still you can keep operating, right? And delay going to service. Okay. And again, as I was mentioning, so there are two possible actions, right? Only two actions, very simple model. So it says it has to decide at the end of each week, you have to decide whether you have to go for service, or you have no need to go for service, right? Service or no service. Okay, so that's the possible actions here. And now, so in this particular example, so if you see both the disturbance and state evolution, it's not always necessary you need to have an equation, right? I've encapsulated both into probability transitions. Okay, so what does this represent? So this says this is essentially denoting what is the probability that the next state is j, given that the current state is I and current action is u. Okay, so that is the referred to as the transition kernel. Just an example here for this car replacement problem. Suppose you wish not to repair. Okay, what would happen? Let's say you are in state 2, you don't wish to go to repair or service. The car will magically cannot become good, right? It may stay in this state, okay, or it may start deteriorating, right? It may jump to one of the higher states. Okay, so that's a simple example. And once you wish to go to repair, we are assuming that whatever state you are in, with probability 1, you will come back to the good state. Okay, so very simple example of state evolution. And what could be one step cost here? So this is the one step cost. Okay, so let's say you wish not to take your vehicle to service. So this is the operating cost. Okay, so it depends. So you may be somewhere here. So C of xk, you still keep continuing. So this is your operating cost. And if you wish to take the vehicle to service, let's say the fixed operating cost R. Okay, so of course you can make it as state dependent also, R of xk, because depends, right? So if the car is completely broken down, the service cost is going to be high. So if it's somewhere in between, so it depends on how much in what condition your vehicle is in. I've just kept it as a simple constant here. Okay, right. So again, so queuing example, right? So so these 5 ingredients should become concrete, right? So then you can model any problem. If you in your problem, if you are able to identify these components, so you'll easily be able to model. Okay, Now, so what could be one model for queue control? One is let's say the beginning or end of the, or let's say the beginning of the day, xk is the number of customers or jobs in the queue. Okay, so or at the beginning of each hour, okay, number of customers in the queue. Okay, now uk, so it could be slow or fast. Okay, so depends on the nature of server, right? So what happens is if you choose to employ a slow server here, okay, so the cost is let's say cs is the cost. Cost in sense you have to pay some amount, right? So let's say cs is the cost, and rate is you can serve at rate ds. Okay, so ds number of jobs you can serve, let's say per unit time. Okay, so in contrast you can go ahead and employ a fast server, is going to cost you more, but its rate is also more. Okay, so one typical example which I have come across is in the context of mess. Okay, so where there is a chapati maker, and suddenly the chapati maker left because he was not getting the amount which he wanted. So then they hired some other chapati maker at a lower price, and we could see the difference now. So it's the trade-off for the mess manager because he has to pay more, right? But then he delayed for some time, and once there was too much unsatisfaction, so eventually he had to hire a fast server. Okay, so these in many contexts you will come across. So these decisions, slow or fast. So now, so I'll call it. So this, what is the randomness here? So number of arrivals that will come, maybe in each hour or in each day. Okay, or by end of the day, right? If it is in the context of bank, so how many customers will arrive by the end of the day? Okay, so that is random, not in your control. Okay, and the state evolution is something like this for a queue. So again, very similar to what we had for inventory control, but here the queue cannot go negative, so that's why we are capping it to 0. Okay, so xk is the number of arrivals. Let's say so in this existing hour, so xk at the beginning of each hour, this is the number of customers. So randomly in the next 1 hour, maybe these many customers will arrive, which is not in your control. And this is uk is whether you have employed fast or slow service there. This is the number of customers that can be served. If it goes negative, we'll just cap it to 0. Okay, it's a very simple model, but in a very more involved model. So even this d of uk is also random. Okay, so it depends on the mood of the chapati maker, how many chapatis he can make. Okay, so it's not so that's also there's some randomness there also. Fine. So but I've kept it simple here. Okay, and now what is the cost here? Cost is the number of them are waiting, and then the cost you have to pay per unit time for whichever server you have employed there. Okay, so these are simple models. Okay, so if you have a model, so if you can abstract it into these ingredients and identify these ingredients, so particularly the state transition is important. Okay, so now so let us slightly get into the mathematics involved here. So I was just talking about one step cost, right? So what is the cost you will incur in one step, right? So here if you ask, so if you want to just minimize this one step cost, right, you may choose whichever is minimum here, right? So C of xk, but that is, so if you choose the server which will which will give you a slow rate, your queue may build up, right? So you may be better off now, but you are not better off in the coming days. Okay, so you have to balance both, right? So both equally well. Okay, so that the trade-off, right? So there is the trade-off. So to capture the trade-off, we'll define this long-term objective, right? So it's not that they the car dealership or the car showroom will run for just 1 month. Okay, so it's long-term goals they have. There may be losses in some months, but they have to make it up by making profits in the coming months. Okay, so so one simple objective is let's say you are in business for many years. So I'll just put it as infinity here. So k is equal to 0 to infinity. Just add up all the cost, one step cost. Okay, so that is the total cost framework. Okay, we call it as the total cost framework. But there is a challenge here. The challenge is that, so this will, if you just add up all the cost, it will go to infinity, right? Unless you are in a setting where those are known as the stopping problems. Okay, So there is some special state when you reach, let's say you will stop the problem. Okay. So for instance, in the case of shortest path problems, right? So think of the deterministic shortest path problem. So you're starting from some state. So and let's say there is a sink node, right? So once you reach your sink node, the problem stops, right? So from there onwards, you can say the cost you are going to incur is zero from there onwards. Okay. So for such special problems, they are known as the stopping problems. So this framework is works well. Okay. But there are other frameworks also. So this generalizes that total cost framework. So this is known as the discounted cost framework. So because the cost, right, so the sum could go to infinity, what you will do is just put a discount factor here, gamma. Okay. So gamma could be in 0 and 1. So let's say your gamma is 0.1, right? So for the first time instant there is 0.1. So then you are squaring up, cubing up and so on, right? So gamma square 0.01, right? So then 0.001 and so on. So this cost will eventually converge irrespective. This may not go to 0. You cannot drive your one step cost to 0, but because of this factor it will go to 0. Okay. So it's very useful in the context of economics, right? So this is very useful in the context of economics. If you see, so if you have some amount of money, so you could, if you invest now, you are going to start accumulating interest, right? So the next time is, so for the next financial year, some interest will be added and so on, right? So that's particularly useful there. Okay. So but this is a very popular framework. So finally, we have this average cost problem. So this in many contexts makes sense, right? So you are interested in the average performance of the system, right? You see, I've just added up, it should have been k minus 1 here, okay? So there are, let's say k minus 1 one's cost, and 1 by k is like the average cost per unit time, right? Just take the limit as k goes to infinity, okay? So there is MDP framework to address each of this setup. So in this talk, I'll mostly focus on this particular framework here, discounted cost. So if you understand this, so then it's easy to generalize it to the average cost framework, although it's slightly involved, right? But I'm not not going to discuss about this one. Okay, so this is slightly advanced, right? So now let's formally address these problems. Okay. So this framework using Markov decision process, okay, problems of this nature using the framework of MDPs, right? So again, so I'll just recall. So these were the 5 ingredients, right? And then, so this is the system. Now, so what I will do is, so there is this random disturbance and also the state evolution. Okay. So these two components, right? So this random disturbance and state evolution, what I want to do is I want to encapsulate both of them into a transition kernel. Okay. So for one of the examples I talked about this, right? So this essentially means probability. So if you take action u at time k and this was your current state, what is the probability that the next state is some other x dash? Okay. So this is the transition kernel. Okay. And then, so this is the reward or cost. Okay. So this is the one step reward or cost in the cost that you are going to incur during time k. Okay. So what we will do is we will look at the cost minimization problem. So I'll just call it as cost. Okay. So if it is reward, you want to maximize the reward. Fine. So what you do then is wherever you see a min, you have to replace it by a max operator. Okay. So I'm just thinking about minimizing the cost. Think of G as the cost, right? So then we talked about discounted cost, right? So we have to formalize it. Okay. So what is the discounted cost? Now let's say a priori at time 0, you make a decision that this is, so you choose something known as a policy. Okay. So what is a policy? Here, so let's look at this equation now. So if my state is xk, you are making a decision that I am going to use mu k of xk, right? Mu k is essentially a function, right? A priori you have decided that, okay, see, if the car is in this condition, I'll take it to service, right? So if it deteriorates so much, I'll take it to service, otherwise I'll not take it to service. So that's one policy. It may be optimal or not optimal, so it's a policy at hand. Okay. So if you see, then I have to decide what are these mu naughts, mu 1, mu 2 and so on, right, even before deploying or starting your car showroom. So you have to decide, okay, what is, suppose if this is, I have 2 cars left with me at the end of the month, how many I will order, okay. So you have to make a decision like that. So I call that decision making as a policy. So this is an offline policy, means even before starting the problem, you just have a policy at hand. Objective is to find the optimal policy, okay, and this X is the initial state that you will start with, okay. So the car may be in good condition, maybe the initial state is 1, right. So you will start like that. So that's the initial state. So this is the discounted cost, okay, and this expectation just represents the it's like average, okay. So it's like taking the average, right. So over all the randomness that is possible, right. So once we have defined that, so once you have a cost in hand or once you have any function in hand, we ask what is the optimal X star, right. So here it's not simple X star, it's essentially, you see, it's, you have to find out this vector of functions, right. So that is your X star. So it's pi star here, right. So whichever policy is going to minimize your cost, so you're asking, okay, tell me what is that policy, okay, and then this is the optimal cost, right. So J star, so is so this policy should give you the optimal cost, which is essentially the minimized cost over all possible policies, okay. So you may be able to compute or not, but it's a clear definition, at least the definition is there, okay. So you may not be able to compute J pi of X for some policies, but still there may be some there will be some J pi, okay. So essentially we are asking what is the cost among all such policies, okay. So now before proceeding further, a couple of definitions that I would like to talk about. So the very important result in this theory of MDPs. So first one thing I want to talk about is stationary policies, okay. First of all, okay, so a Markov MDP problem is said to be stationary if the transition kernel is stationary, okay. So that means, essentially it means that your system is not changing with time, okay. So transitions, right. So even after 1 year, we are assuming that the number of customers arriving is stationary, okay. It's a simplification, but in suppose when systems do not vary for a long time, so this is a reasonable justification for such systems. So you can assume that your MDP problem is stationary, okay. Now a policy pi is said to be stationary, okay. So if you use the same mapping at every time instant, right. So that says that your policy does not change with time, okay. Suppose your car is in good condition today, okay, and you decide not to take it for service. So even tomorrow, if it is in the similar condition, you will not take it to service, okay. Okay, so so a policy is stationary if the decision doesn't change with time or the decision function doesn't change with time, okay. So now this becomes, we have slightly simplified the problem, right. So if you look at this part here, we are thinking of identifying mu naught, mu 1, mu 2, mu 3 and so on, right. You have simplified it now. All you need to do is just identify one function, okay. So now is that good enough, okay. So here is the result. So what there is a theorem which says that for a stationary MDP problem, there is an optimal stationary policy. You need not look everywhere, you just look for one stationary policy, okay. So that's going to be optimal, okay. So that's a very important result. It will reduce lot of our work. So it says, so I'll just define that the cost of that stationary policy as J mu star. So mu star is that stationary policy. So J star is the optimal cost anyway, and that optimal cost is still minimization over all possible policies, including non-stationary. You may wish to use a non-stationary policy, so that's well and good, right. But I can give you a stationary policy that will achieve the performance as good as a non-stationary policy, okay, right. Okay, so the next two slides, right, although you will see some notation, but it's not very heavy once you have followed until this point, right. But that will form the essence of the MDP formulation, okay, and it's not very difficult, okay. So let's have a look at this, right. So if you have a policy, stationary policy mu, right, which will say that, okay, if you are in state xk, mu k of xk is the action that I am going to choose, okay, and this is the discounted cost for that particular policy mu, Okay, if you see carefully, so this is the discounted cost, right? So I'll write it in two parts, right? I'll extract the first term, k is equal to 0 term, gamma power 0 is 1, so I've just left it here. So I've just extracted it out, right? X is the initial state, mu x is the action that I will take when I'm in the initial state, right? So then what I will do is I'll pull this gamma out, right? And these are the remaining terms now. Okay, so there's gamma power k. I just pulled this gamma outside that summation. Okay, so gamma power k. So what happens now is, so look at, see, you can carefully stare at this term and this term. Okay, they are identical. So anyway, the sum is running to infinity, right? The infinite terms in both summations, and you can just do a change of variable k minus 1. You can call it as L. Then you will have L is equal to 0 to infinity gamma power L that you have now, right? So now that's very interesting. Okay, so here is what you can do now. So what you can do is the only see here. I knew the initial state. I knew that the car was in good condition, right? But this is the second step, right? K is equal to 1 is the, okay, 0th step was there, then step 1 was there, right? So what happens when k is equal to 1? I do not know whether in the next week the car will be in good or bad condition, okay? But still I can put this probability here. So x dash is the state, next state. So with some probability I'll go to x dash, okay? And suppose you continue that policy from there onwards. So this is the cost you will incur from day 1 onwards. Okay, so this was day 0, so this is day 1 onwards, right? So if you understand this equation, so MDP essentially means you have understood MDP. Okay, so the iterative equation here, right? You see, or it's essentially a fixed point kind of equation. So even on the left hand side you have a j function. Essentially this is the unknown function, but you have the unknown function on both sides. Okay, so these are known as fixed point equations, but there are methods to solve these fixed point equations. Okay, right. So now, so this is actually the one step cost and this is the future cost to go. You see, if you try to optimize your one step cost, you may end up in bad state on day 1, and you might incur your future cost may be bad. Okay, so if you take a bad decision may be good for today, right, but it may lead you into a bad state tomorrow, right? So that's not good enough. So you may, so that way you have to trade off between two. You should be able to work hard today so that the future is good or so on. Okay, so similar examples, right? So you have to take some risk today, right? This cost may not be optimized, one step cost, but it may be good. You may land up in good states in the future. Okay, so that's so you have to trade off between these two. Okay, now so this is the next slide, which is also very important. So now here is the trick actually. Okay, so I'm just there are a lot of theory behind this, but I'm just doing it in a hand waving fashion here. Okay, so here now suppose magically I will tell you, okay, what is the optimal value function. Magically I will tell you, okay, see, this is the optimal value function. Okay, and that I will not tell you on day 0. I will tell you, okay, today you do something, from day 1 onwards I will tell you what is optimal, right? Right. So you will suppose, let's say you are going to use some policy. So this is the cost you will incur on day 0, and day 1 onwards you can do optimal. Okay. So I'll give you an example also, right? Now, so think of it like this, right? So now let's say from Tirupati you want to book a flight to New York. So you'll go to a travel agent and you will ask him, okay, I want to give me the best price possible. So maybe the travel agent says, okay sir, I do not know from Tirupati, but if you ask me from Hyderabad, Bangalore, Bombay or Delhi, I can tell you what is the best price from there onwards, right? So maybe travel agent just has that information. So what would you do then, right? So now you will see so the cost of going from, let's say, Tirupati to Bombay is cheaper, right? But you will not choose that flight, right? So you will ask what is the flight cost of flight from Bombay to New York, right? You will add up both of these costs. That will give you the effective cost, right? So let's say from Bombay onwards you need not worry. So the routing is made, right? So now you will add up all the 4 costs, right? So they essentially the shortest path problem, right? So you'll find out yourself what is the best price to go from here to Bangalore, and Bangalore you will add up Bangalore to New York, right? All these, and you will compare which will give you cheaper cost. You will choose that one, right? So that is essentially what mu would be optimal, right? So then you have to solve this problem, right? So what you will do is this one, Bellman equation, right? So I was talking about shortest path, right? So once we hear Bellman, so there is the Bellman-Ford algorithm, right? So the Bellman-Ford algorithm is actually a specific case of this more general equation. This is known as the Bellman equation, right? So now, so if you give me the best policy from day 1 onwards, so what I will do for day 0 is I will choose that action which will essentially minimize not just this cost, not one step cost, this plus I should ensure that I will go into good states into the next day, right? That probability also is taken care here. So I will try to find out that action which will minimize some of these two costs, okay, one step cost plus future cost to go, and that should actually be optimal, okay. So that is J star, right? So these here, and what is the best action now? If you are in state X, the best action to take is you choose that action which minimizes. So arg min means that, right? So min will say what is the minimum value of this quantity. Arg min will say what is the value of x star. If you have function f of this is like f of x star, this is like returning back the value of x star, right? So if I give you a function and ask you what is the optimal, so you have to give me both, right? You have to tell, okay, f star is optimal, then I will tell you, ask you at what point you will achieve that optimal. So you also have to tell me that point, right? So that is this here, okay. So this is if you understand this equation, so that means you know MDPs to some extent already, okay. Now the challenge is, so how do you solve this fixed point equation, okay? So as I told, no, it's fixed point essentially means both, so there are unknowns on both sides, okay. So there is a j function here. To calculate this j function, you should know the j function, right? So that's a fixed point equation. There are ways to solve this, okay. So I'll if your state space is finite, what you will have is you will have some set of equations which may not be linear because of this min operator, okay. So the min operator is making life complicated, okay, but otherwise also you have some set of equations, okay. So and then you, in fact, if you remove the min operator for each u, you have to solve this set of linear equations, and then you will be able to, there are some methods like that, but I will talk about more workable methods. So one is the value iteration algorithm, right? So we are now, our objective is to solve this equation here, right? So now this is a recursive equation. So whenever you see a recursive equation, without worrying whether it will converge or not, just do the value iteration like this. What you will do, you will suppose you have a function of the form x is equal to f of x, you have to find out the fixed point. You have to find out, let's say, x star which satisfies this equation. What you will do is you will start with some x naught, find out f of x naught, call that as x1 and so on. It's very similar. So what I will do is I will find out this initial, just initialize it to 0. It could be any arbitrary value, doesn't matter, right? And then what I will do is using the previous values of j function, I will start from 0, right? I can find out j1 now. If I plug in k is equal to 0, I will get j1. I will just solve this. I will go for j2, j3, so on, right? And hope is that it will converge. So there are some conditions under which it will converge. So when you are implementing it as an algorithm, so you will terminate when these two cost is less than equal to epsilon, okay. So you will just put some tolerance, maybe 10 power minus 3 or 10 power minus 6, and terminate whenever they are close enough, okay. And so what happens is after termination, the hope is that your j star will be very close to, so your jk, whatever the value at which you terminated, no, that will be very close to j star. If your epsilon is small enough, it will be very close to j star, and if your epsilon is small enough, your mu star also will be very close to the optimal policy. In fact, in finite settings, finite in sense your actions are finite, state is finite, your mu star will be actually equal to the optimal policy, right? In the finite space, suppose there are only two actions, right? So now it should be either this or that, okay. So once jk is very close to j star, right? So you will mu star will be, you will exactly be able to identify mu star, okay. So this is the value iteration algorithm. So there are also another algorithm referred to as policy iteration. So what you will do is you will fix some initial policy, okay, you will fix some initial policy mu naught, and what you will do is you will compute the value of that policy. If you remember, for a given stationary policy, what you will do is, see, I will use mu k, and here if you look at this equation, one step cost plus future cost to go, right. Now how do you solve this? So these are essentially set of linear equations, right. There is no min operator. You can, so this is one set of equations. You will be able to solve this easily, right. Otherwise you can use value iteration just to solve this, okay. Then you will improve the policy, okay. The policy improvement is something like this. So what you will do is, see, the next policy is will come from this equation. So this should actually be j of mu k, right. So you will choose that action, right, as your next policy that will optimize this cost here, one step plus future cost to go, where the future cost, instead of j star, you have now this earlier policy, okay. So this way every time you will keep improving your policy, and you will terminate once you will get back the same policies in 2 iterations, okay. So you will terminate, and once you terminate, the optimal value and policy, right. So your mu k will be the optimal value, and j of mu k will be the, sorry, mu k will be the optimal policy, j of mu k will be the optimal value, okay. So these are essentially two algorithms, okay. So value and value iteration and policy iteration, right, right. So we are able to identify the optimal, right. So what is the challenge here, right. So where is the learning aspect coming here, right. So now here is, so let's carefully look at this Bellman equation, right. So what is unknown here, what is challenging to know here, right. These transition probabilities, if we know that the work is over, okay, we need not do any learning or anything. The thing is, these transition probabilities are unknown, right. You cannot, it's not easy to predict how many customers will arrive in a day, okay. So these are all random, right. So transition probabilities are unknown. So here in the case of inventory control, right, how much of demand you will get in that particular month, that you cannot, it's not easy to know, right. You cannot predict that, or you cannot put a distribution on that so easily, right. And similarly, you do not know how your car will break down, right. So that also is not easy to tell, right. You cannot tell that it's in good condition, maybe suddenly it can break down. So all possibilities are there. You do not know these distributions, right. So in real life, so the probability distributions are not easy to know, right. It's impossible to know also, okay. And then, so there are so that's the challenge here, right. Even in the queue control, I do not know number of jobs that will arrive or number of customers that will arrive in a given time period, or in a given hour. I don't know how many customers will arrive into the bank, okay. So these randomness, right, we cannot, so we have to live with the randomness, and moreover we do not know their distribution also. So now we have to start learning those unknown distributions, okay. So reinforcement learning is essentially about that, right. So now once the MDP framework is clear, so RL is a natural process, right, reinforcement learning, right. So you suppose for your model, if you know the transition probabilities, no RL is required, okay. But in many instances, right, real life instances, we will not know those transition probabilities, right. So that's why we have to talk about reinforcement learning, okay. But even for RL, the Bellman equation forms the mathematical basis, okay. So you want to solve this equation only, right. Thing is, you do not know these transition probabilities, fine. So let's not, let's say we do not know. Now what we will do in RL is not just this transition probabilities. So essentially we will just try to estimate this entire function here inside, okay. So I'll call that as the Q function. So that's where this Q learning comes from, right. And be careful, this Q is not same as the queue control problem that I talked about. So that's the queue, number of people lined up in the queue. So this queue is different. So this queue is just because the notation is queue here, okay. So there is some meaning for this queue, okay. So it's a so somewhere this notation comes from, but you just be careful, okay. So queue learning is about learning this queue function, okay. Now let's see, here is, I'll just propose an algorithm as to how you can estimate this Q function. Okay, so learning the Q function. So what you do is, let's just initialize. So Q tilde is like the estimate. I'll just initialize it to all 0. Okay, so 0 I'm just taken as an example. So it could be arbitrary. Okay, you can arbitrarily initialize it to any value. Doesn't matter. Okay, so now what you do is, now let's say somewhere, so there's some way of estimating this or updating this Q function. So we'll come to that update later. So suppose if these are the true Q values. Okay, so if Q tilde, if this is the correct, or if Q tilde is equal to Q, and at time k, what action would you pick? You will just pick UK, which essentially minimizes that action which minimizes this Q function once you fix xk, right? So essentially the Bellman equation, right? But this may not be the exact Q function, but nevertheless, let's assume that this is the Q function, and let's pick this Q tilde value. Okay, so we'll pick this action. Now here is the key step. Okay, so I could have started the RL algorithm from this update equation, right? But to make sense of this update equation as to why this update equation, so we required all that mathematical basis. So now what you do is, see what has happened is at time k. Okay, so let's say think of it as time 0, your initial Q values. Okay, you pick some action and you move to time k plus 1, time 1. Now what you do is, you will now update here, right? So this was the previous state, this is the current state. You moved from the previous to the current state. Now you have to update this value. You took action UK, right? So the update procedure is like this, right? With so there is some parameter alpha k here. So with so 1 minus alpha k, you will so think of it like with probability 1 minus alpha k, I'm going to retain the old value. I'm not going to update my Q tilde value. And then with some probability alpha k, so this is the new value of Q. So this is a new estimate for Q. Okay. Now, so either you will use the old estimate, okay, or new estimate. Suppose old and new estimates are equal, okay, so then you will get back this equation actually. Okay. So this is an approximation for this particular equation. Once all the Q values have converged, so you will essentially get back this Bellman equation. Okay, so that's the essence of this update equation. Okay, so let's slightly dig into this equation. So let's look at this parameter alpha k here. So again, like any learning algorithm, so there are parameters here, right? So it's about identifying the right, using the right set of parameters. So what happens is, what is this quantity alpha k? Okay, so it's essentially used to trade off between old and new estimates for this Q, right? So if you use a small value of alpha k, what would happen? Essentially you are ignoring this term, you are giving more weightage to the existing estimates. Okay, so that is known as conservative update. Okay, so you are not ready to update your Q values, right, quickly. Okay, you are very conservative about updating, right? So if value of alpha k is close to 1, what happens is, you are giving more weightage to this term, right? So you are aggressively updating. Okay, so you are updating very aggressively, right? So now there is a trade-off, right? So the ideal choice is like this. What you should do is, see, initially you have not started learning, right? So you have to be very aggressive. Your Q values should not have converged. You should aggressively keep updating. But after some amount of time, your Q value would have started converging. So you should then become more conservative. So what happens is, you should do a gradual progression from large to small alpha k, right? So something like this is preferable, right? So, or even any sequence that gradually decreases is also works well. But I generally prefer this equation here. What happens is, alpha k is 1 by this eta. So this is the count function, that is essentially how many times it keeps track of how many times you used action UK when you were in state xk. Okay. See, suppose if this number is large, what happens? Alpha k is small. That means large number of times you have used this action here, right? So your Q should have sufficiently converged. So you will become very conservative. Your alpha k is small. You will stop updating that particular value of Q now. Okay. So that's the essential idea here. Okay. Fine. So there is one more concept about RL that is very important. So what is happening here is, see, here I am claiming that, okay, let's at time 0 onwards, let be greedy. So this is always greedy, right? So I do not know, this may not be the exact q values, at least in the beginning of the algorithm, but I am trying to be very greedy here. Okay, I am just trying to choose that action which is the best given these estimates of q, without even worrying whether these estimates are good or not. Okay, so then what you do is you can do a modification. So this is known as epsilon greedy, where you with probability 1 minus epsilon, you are going to be greedy, but with remaining probability epsilon, you are going to randomly start choosing some action. So once in a while, you have to start exploring. Okay, so that's the exploration versus exploitation trade-off that even Dr. Manjesh was talking about, right? So always, so with some probability, you should start exploring. Okay, randomly you will choose one of the actions, and then for most of the time you can stick to the greedy action. Okay. So again, here I have shown epsilon to be constant, but it can vary with time, right? So what can happen is initially you have to explore a lot, right? So your epsilon k could be large, right? But as time goes on, hope is that you would have already estimated the q values correctly. So then you will start decreasing your epsilon k values, okay? So that you will start exploiting more now, okay? So again, these are all set of parameters, and your RL algorithm is very sensitive to all these parameters. Okay. So in the remaining time, I will just talk about one application that we have worked on, right, in the applying RL to problems in wireless networks. Okay. Yeah. So maybe, yeah. So we can proceed. Yeah, so this is so we had worked on this problem of achieving coexistence between LTE essentially the 4G technology, okay, or the cellular technology, and Wi-Fi. So Wi-Fi is the existing Wi-Fi, okay, and then so we are using reinforcement learning to understand how to achieve coexistence between these two, and this joint work with my so BTech project student Chaitanya, okay, so he is currently at is TCS labs in Hyderabad, and now he is going for a PhD at University of Illinois at Urbana-Champaign. Okay, so this was a work with Chaitanya. Okay, so right now, so what is so let me just set up the context actually. So what was the motivation for this work is see, there is always the demand for mobile data, right, is continuously increasing, and that's because we have all these video applications, right. So these days, if you see, the calls are never over audio, right. So we always want video chat and so on. There's live TV, and live gaming is also very popular. Okay, so the lot. So we recognize that there is huge demand for mobile data, and there are some solutions. Okay, right. Already the people are working on 5G deployment and so on. So right, so you can increase the throughput, right, directly by deploying 5G. There are other techniques also, data offloading, but the technique we were interested in is referred to as LTE unlicensed. Okay, so what it says is why not allow the cellular operators to use the existing unlicensed band. Okay, so Wi-Fi is operating in something known as the unlicensed band. You need not pay for that band. Okay, so licensed band on the in contrast, you have to pay for that band and get license for that band. Okay, so now since Wi-Fi is not deployed everywhere, right? So randomly in some forest region, Wi-Fi may not be deployed, or if you go to playground, there may not be Wi-Fi, right? So why can't cellular operators use that band, right, to transmit and get higher throughput, right? So right, so that's the that was the primary motivation. So LTE unlicensed. Now the challenge is how to achieve coexistence. Okay, so what is the yeah, so how to achieve coexistence, and so these are some of the subsections. So we'll go into those things here. So first is let us formulate something, right? So before even you can formulate a RL problem, so let's formulate a model precisely. So now, so right, so what is happening is so we'll assume a very simple model to begin with, so we can scale it up actually later. Okay, so let's say there is one LTE base station and one Wi-Fi access point, and now the challenge is this one, right, the medium access control. Okay, so what LTE does is it uses something known as a schedule based MAC, right. So whenever, let's say, you are going to download some amount of data, what the LTE operator, there is a central controller, and there are, if you know about OFDM, so there are OFDM resource blocks. Some number of blocks are allotted to you. It's like a centralized controller. Okay, it's like a teacher in classroom deciding which student should go first, which student should go second, and so on. Okay, so it's something like that, right? So the centralized controller based. But Wi-Fi on the other hand, so there is no control, centralized control, right? So if you take your, let's say some of you may be browsing, right? If you use your phone, now if everyone is in the same room or browsing, now if everyone starts transmitting simultaneously, okay, there will be collision at the Wi-Fi access point. So instead what you do is some kind of randomization is happening in Wi-Fi, okay. So each one will wait for some time randomly before he can start transmitting, okay. So that will avoid collision, okay. So that is what is happening in Wi-Fi, and such that MAC is medium access control, is referred to as contention based, okay. Now these are like two different technologies. Now thing is, how can they share the spectrum, right? Unlicensed, available unlicensed spectrum, okay. So what we do is we adopt this, the simplest way is to duty cycle, okay. So both are two different technologies, both can start duty cycling here, right. So what we can decide is the LTE can choose to transmit for some amount of time in a frame. So time is slotted into frames, and within a frame the LTE can choose to transmit for some amount of time, and at that time, so it can stop transmitting on and off. LTE can go on and off, and during this time Wi-Fi users will get some throughput, okay. And the interesting part is the Wi-Fi is designed such that if some transmission is going on, Wi-Fi will become silent, okay. So Wi-Fi is inherently designed like that, okay. So it will not force a transmission when it detects some energy in the in that particular frequency, okay. So there is frequency band allotted to a Wi-Fi. Whenever there is energy, so it will just back off from transmission. So that way Wi-Fi, there is no modification required. So what LTE can do is it can just start transmitting for some amount of time, but during this time Wi-Fi will just remain silent. Its users are not going to get any throughput, and for the remaining time, so LTE will remain silent, Wi-Fi will start transmitting, okay. So that's the model here. So T is the duration of the frame. So this is what we want to identify. Beta k is what fraction of time LTE should transmit in a frame, and what fraction of time Wi-Fi should transmit, right. Essentially you want to identify this beta k. So for frame 1 it is beta 1, beta 2, and so on, okay. So that's the decision problem here. So now it's a sequential decision problem, right. Now the problem of coexistence just reduces to this problem of choosing appropriate air times, okay. So of course there is a trade-off, right. So if you choose a large value of beta k, so what happens is you are unfair to the Wi-Fi, right. So large value of beta k means LTE will get all the throughput in that band, Wi-Fi will not get any time to transmit, right. But that's, so you have to make sure that even users connected to Wi-Fi also get some throughput, right. Otherwise it's not fair. Now small value of beta k will give more time for Wi-Fi, but LTE is going to lose in the process, right. So LTE is going to get will not get any throughput, right. So that's the whole purpose of LTE unlicensed is lost. So how to choose beta k in a optimal fashion, right. Now, so here what I will do is I will set up the model. So model is involved. So I'm not expecting you to completely understand the model. So what my objective is, if you can recognize what is the state of the system, right. So there are 5 ingredients, right. I want to introduce those ingredients, okay. Now what we are going to do is we are going to model LTE and Wi-Fi as a queue, okay. So there are some number of packets arriving at the LTE end, so they will start queuing up, okay. So that's our assumption here, right. So there is some arrival and service rate at the queue, right. So now here look at this frame, right. So here packet A has arrived, and this is the LTE time, right. So this is the Wi-Fi time, LTE is on here, it will start serving packet A. Once packet A service is over, it will start serving packet B, C. It was serving packet D, but then it has to stop here because Wi-Fi will start transmitting, right? And now during this time packets can arrive. These are the LTE packets which are arriving here, right? And then again at this instant Wi-Fi will go off because LTE will start transmitting, okay? So again it will complete the service of D, packet D, and then it will take a packet E which arrived during this off time, and then so on, okay? So that's the model. So that's the model we are assuming, okay? Simple queuing model, okay? So there are some assumptions of course here, it's not very realistic, but nevertheless we will see what is the optimal air times that this model will yield, okay? So Wi-Fi on the other hand, we have to be slightly careful in modeling Wi-Fi. So the way Wi-Fi operates is like this, right? So let's say packet B and packet C has arrived when the LTE was on. Now the LTE is off. Now suppose see Wi-Fi essentially like packet B may belong to one user, packet C may belong to another user. So if Wi-Fi starts transmitting both these packets, right, or if both both these packets at same time, so there will be collision, okay? So what Wi-Fi does is instead each of these packets are going to wait for some amount of time randomly. Each packet is on its own now, okay? Each packet has to attempt transmission on its own. What they do is you will like randomly think of some, you will randomly pick a time, okay? So let's say suppose if I ask 2 or 3 of you to speak, right? So if you speak simultaneously, there is going to be collision. So one algorithm to break the collision is like this. I'll ask you each one to pick some random time, put a counter, right, put a timer. Once the timer counts down to 0, whoever counts down to 0 first will go and start speaking, right? So that way the chance that all of you will pick the same random number is less, okay? And because of that way we can avoid collisions here. So that's what Wi-Fi does, okay? So now there is random time and the order is not maintained, right? So although packet A came first, but packet B has won that contention, okay, and it will transmit, okay? So packet B is transmitted. Then similarly, now only A and C are left, packets A and C, so they will also contend. Now packet A has won the transmission and so on. So it's like unlike the LTE, right? So LTE was like first in and first out. So Wi-Fi is different, right? The packets are not served in the same order, and between this both services, so some randomness is there, some random amount of time one has to wait before the actual service can begin, okay? So there are other technical aspects, so I will not go into those details, but essentially now we are setting up what is the state of the system, right? So this is your, see this is the way, right? So x-axis is like, think of it as time, so the essentially time. So y-axis is number of customers in the, or the number of packets in the LTE queue, okay, that is NL, okay. Now you see what happens is whenever there are 2 packets here, when a packet service ends it will fall to 1, a new packet may arrive, so it will go to 2 again and so on. You see it will keep alternating here, right? So whenever a service ends it will fall down, whenever a new packet enters it will go to, it will increase. And now here since the LTE is off, right, LTE is off, so packets arrive, they do not get service, so queue will start building up here, okay. And this is the end of the frame, and this is the worst case scenario, right? At this point the queue would be maximum, right? So I will pick this number, right? So there are 4 packets waiting in the queue, okay. Similarly for the Wi-Fi, so what happens in Wi-Fi is it is waiting here, so there is no service happening, so queue will start building up, and at this transition phase from on to off, the queue length will be maximum for the Wi-Fi, okay. And when the Wi-Fi will get its chance to service, so the queue will start decreasing now, because some services, some packets, right, are getting serviced, right. So now you see now the sequential addition problem we discussed, right. So the simple state xk I told, right. I never told that xk should be a scalar always, okay. So here xk is these numbers, actually pair of numbers forms xk, okay. So state can be anything, it could be a vector also, okay. So this is your system state. Now what happens is, let us see xk plus 1 is 4 comma 3, why 4 comma 3, it is all integers. 4 because 4 packets of it represents that 4 packets of LTE are waiting, 2 packets of Wi-Fi were waiting, that was the maximum you reached, okay. So this is your state of the system. ideally what should be there? It should be 0, comma 0. Okay, because that means no one is waiting, everyone got serviced, so everyone is happy. So you have to choose beta such that this number will be low. Okay, that's the objective here, right? So I just introduced some transition probabilities and so on. Again, some of these things, right? So policy, again, I'm going to define all these things, policy, and so what is the state, and also this is we have done, and we'll essentially look at stationary policies. So this is something I talked about already. Okay, and now these things should become clear, right? So what is the discounted cost, right? Discounted cost. And what is this now? So if you remember in the original formulation, I had g of x comma action, right? X comma u. But now what is my one step cost? See, this is the, I'm calling this as the maximum queue length here, right? So I'm going to add up both of them, right? So W1 and W2 are just some weights actually. You can think of it as 1 and 1 also. That means I'm just interested in minimizing sum of both queues. So number of packets in both queues. Okay, so that's the objective there, right? So then yeah, so we'll go to the RL framework now. I think many things now. So again, I just written down the Bellman equation here. Okay, so the same sequence you will see. Now the action space is, what is the beta, what is the on and off, on time you have to choose, or fraction of on time, right? So that's some number between 0 and 1. It's a very involved. So this is like action space is huge now. Okay, but still you will be able to write down this Bellman equation. Again, so as I told, no, so this is the one step cost and future cost. For instance, see, you have to choose beta k very carefully. Okay, so now suppose x1, okay, x1 is large and x2 is small. Maybe you have to start increasing your value of beta so that you will give more time to LTE. Okay, so x1 is large means number of customers of LTE are more that are waiting, right? So you will make beta large, okay, and so on. You have to anyway trade off between these two quantities. Okay, so again the same set of equations will be there, and so this is the same theorem. Okay, so which says that any if you can identify this j function, somehow solve this j function, so then that is optimal. Okay, so that's what this theorem says. So yes, again, so these probabilities are not easy to compute. Okay, so that's why we go for the RL framework. Again, the same equation. Okay, so it's the same algorithm, right? So now that we know this algorithm, so I'll not go through this, but you look at the Q estimates. So this is my current state. So this is my next state, and this is how I'll take actions and so on. And so this is the Q update equation. Again, the epsilon greedy algorithm. Okay, so maybe yeah. So I think in last 5 minutes or something, I'll wind up. I just given the pseudocode of the RL algorithm here. Okay, right. So let's check some simulation study here. So we have done some simulations. So our frame duration, we say that is say 2 time units, and these are some arrival rates and service rates, right? So this is the number of customers of LTE that will arrive on an average per unit time. Okay, so this is the number of customers that can be served per unit time. Okay, so so that those are some of the setups. So these are, again, there are a lot of parameters here, right? So these are the weights. So you have to choose a discount parameter. Then contention window is something to do with Wi-Fi. Okay, so if contention window is large, the duration between successive packets, right, is going to be large, right? So that's what this represents, contention window size. Now so these are some algorithms that we have implemented. I call it as the Q learning initial phase. Then it's essentially the same algorithm, right? So Q learning initial phase. So then what we did also is Q learning steady phase. What we do is once these values of Q, the Q estimates are learned, okay, we'll reset time to 0 at that point and again start looking at what is the performance of our algorithm, right? Essentially, alternatively, you can think of it as starting with not Q is equal to 0, but from the converged values, right? So the values of converged, you will start from there, right? Then these are heuristics. Constant beta is, let's say someone chooses that, okay, I will not worry about all this, I will fix beta is equal to 0.5. I will give half of the time for LTE, remaining half for Wi-Fi. Okay, so that is the constant action, right? And then random action is, it says that okay, I will not do all that, I will just toss a coin and I will choose randomly, I will pick a number between 0 and 1, I will call that as my beta in that slot. Okay, so these are all heuristic algorithms, right? So now here is some results here. So what is happening is, see, this is the this is like time, actually frame index. So this is like time, and this is the discounted cost. And now what we see is so the learning algorithm, right? So the steady state algorithm, okay, steady phase algorithm, so gives better. So this is the cost, you have to minimize the cost. So this is the other algorithms. So this is also the learning algorithm, but this is starting with unlearned q values. Okay, so this is the learned q values, will give a lower discounted cost, and the heuristics do not do good. Okay, so for instance, if you fix a point, if you give half of the time to LTE, half of the time to Wi-Fi, that is CA 0.5, so you see the cost is higher, discounted cost. Okay, right. So there are other settings also we have seen. For instance, here if you see, I am varying the weights also, right? And as we vary the weight, so you see this learning algorithm, right? So the blue algorithm QLIP, right, is only in some regime it's doing good, but the red algorithm, which is the steady phase algorithm, right, it is actually, you see, it is kind of doing the best of all the policies. Okay, so it is able to nicely study which is the best heuristic, and it's going to follow, trace that best policy here. Okay, yeah, achieves the best CA beta algorithm. Okay, so there are few more with few more factors we have varied, actually contention window size and so on, and we show that it's not always, see here it looks like a constant yeah. So I think I was almost at the end only. So yeah, okay, yeah. So it looks like a constant the constant beta algorithm always does good, right? It's trying to trace that, but that is for some specific values. Now once I vary the contention window size, it's not easy to guess actually which constant algorithm does or which heuristic does best, or even if there is a heuristic which will do good. Okay, so the learning algorithm is very useful in these contexts. Okay, right. There are some future scope for this work, right? So QLIP needs some improvement, it's not doing good, but QLSP is essentially is like rebirth of QLIP. Okay, so but QLSP does good. Then there are a few other yeah, so they essentially the summary. So I think yeah, there were some directions for future scope. In fact, our lab, we have done some experiments also using USRPs and Wi-Fi access points. So the small prototype that we have established there. Okay, so with this, I think yeah, so I've come to the end of my talk.
Thank you, sir, for this talk.